Okay, so what I want to do then is show you how you maybe take this really simple surface ij thing and maybe extend it to something incrementally more complicated, and we'll see then how that works. So let's look at a three-surface network. I've got three surfaces here. I'm going to say that we're only concerned with the radiation that's occurring inside. So whatever's happening on the outside surfaces, maybe they're in contact with something, it's conducting away heat or whatever, but there's only radiation present inside this enclosure. So there's three surfaces all exchanging radiation. And what I want to do is draw like a resistance network that describes this. So let's represent each of these three surfaces as nodes. And why can we do that? I guess we can do that because we're saying each of the surfaces is isothermal, right? It's all got the same temperature everywhere. So we just treat it like it's a single lumped node. And then what we want to do is draw resistances. So I know from, let's give these labels. So this over here would be surface I. Let's call this surface J, and let's call this surface K. So I know from surface I to J, there's some view factor and a resistance that goes with that. So I'm going to call that RG I to J. Likewise, I could go from J to K. Another geometric resistance, RG, J to K. And I can do the same thing from I to K. RG, I to K. Right, so these are three different resistances, but this is the network that describes how they're all related to each other. I can compute the resistance if I know the view factor and I know the areas, right? So what do we do with this? Well, it turns out to solve this resistance network, we kind of need equations to go with that. And we need to know something about what's happening at each of these nodes. So let's come up with, invent some circumstance, and then we'll kind of solve for that. So first, let's say this surface down here on the bottom is adiabatic. Okay, adiabatic, surface K. Does that mean that there is no heat flowing from J to K or I to K? No. Like you can still have heat flowing, but what it's saying is that the heat that's flowing to that surface has to equal the heat that's leaving that surface. All right, so the net is zero. All right, so surface K is adiabatic. Let's say, what do we know here? So let's say we know that, let's say we know that there's some heat coming in here. Let's call this Q dot I. So this is some heat that we know coming into the problem is being sort of forced across this surface. So maybe there's like conduction up to the surface and then it's radiating into this enclosure. And then let's say we don't know, but we'll just describe it, but there's a Q dot J over here. This is a heat that's leaving. So maybe we need to calculate that value. So first of all, okay, so we have all this information. There's one more thing that I want to do to kind of fully describe it, and that is let's put some labels or conceptual labels on the nodes. So if I'm trying to solve this problem, what am I trying to solve for? Q dots and emissive powers. So I'm going to label each of the nodes with their respective emissive power label. So this one here would be EBJ. This one here would be EBK. And then over here we have EBI. Okay, so we've got this three-surface problem. And what I can do now is, let's say I want to compute things that go with this, maybe the total heat transfer from surface I to surface J, or the temperatures that are involved or something like that. So what I want to do next is, and what you would want to do in this situation is actually kind of draw out the full resistance network. So we've kind of got the representation over here, but maybe another way to think about it is if we were to just sort of draw it out like we typically do. So let's say we have here EBI, that's my first node. And then I'm going to have resistance over here, and this is going to go to EBJ. And then the other pathway is to go from, sorry, let me label this. This is RGI I to j. So I'm trying to figure out sort of like how much heat maybe is going directly from I to j. And to do that, I have that resistance drawn there. The other pathway that heat can take to go from I to j is to go via the second surface, right, or the other surface. So that's going to involve two resistances. So one is to go down here. This is resistance RGIK. And then I have the second one here, which is RG from J to K. Right, this node here is EBK. And then I had, let's see, coming in here, I have a heat transfer Q dot IJ. Let's call this Q dot IJ total. Let me just see how that worked out. IJ total. Yeah, I'm just going to leave it like it was, Q dot I to J. And then, let's see, leaving out of this, we have Q dot, let me just be clear here. So this is where you kind of get into trouble. I'm already getting into trouble. So what we want to do is we have to separate out the heat flows and kind of describe them in some meaningful way. So I've drawn in Q dot I, I've drawn Q dot J. What I care about is like the total amount of heat that's going from I to J. So for that, I want to notate that this is Q dot from I to J total. And that might be different from Q dot I. All right, so Q dot I to J, I will keep this as total. That means since there's no heat being added at K, right, that's an adiabatic surface, what's leaving is also IJ total. Okay, so it's a little confusing what I just did, but basically what I'm doing is renaming those heat flows to be something specific because I now know by looking at this problem that those have to be the same thing. All right, so I'm just sort of renaming them a little bit. Okay, so why am I doing this? Well, we're trying to come up with some equation that helps us solve for the heat flow. So I can do that if I write this rate equation. So let's say Q dot Ij total is equal to the potentials, the difference in potentials between these two things I care about, I to j. So it's going to be EBI minus EBJ. And then I have to divide by the resistance. So what's the total amount of heat flow? It can be either directly from I to j, or it could go I to k to j. So there's these two equivalent pathways that heat can go. So to capture this, I need the total resistance, right? The total resistance associated with both of those pathways. So this would be RG IJ total. RGIJ total. Okay, so then a couple things to point out. I did not involve EBK in this yet, right? Just like when you have like a multi-node resistance network in a classical setting, you don't have to have like an equation related to every intermediate temperature. Here you can just write things in terms of the terminal potentials as long as you're capturing all the resistances along the way. So I did that, all right, so we have that, the potential is just I and J here, and then I have the total geometric. So we now have to figure out how to calculate that total resistance. So RG IJ total is going to be equal to all the different ways in which he can go from I to J. So pathway 1 is going to go through RGIJ. Pathway 2 is going to go through RGIK and RGJK, right, like this. So let's just write that out. So it is something like this. We have two parallel pathways. So I'm going to do 1 over RGIJ. The other pathway is 1 over the series resistance of the bottom two. So this is RGIK plus RGJK to the minus 1. By the way, on the last exam, I think a lot of people, or a larger than should have been number of people, didn't remember how to calculate parallel resistance. This is how you do it. Okay, so it's 1 over the first plus 1 over the second inverse, right? Yeah.
Times the area?
Yeah, this is a very good question. So does it matter, in other words, does it matter if we would have written this RGJK versus RGKJ? Right, maybe somebody can see that, but if you remember this idea that Fij is times AI is equal to Fji times Aj, then as long as I'm consistent, well, let's say, as long as I account for the area, remember the resistance is the product of the view factor and the area. So what this is saying is if you went either way, it's the same thing. They're equal, right, through reciprocity. So it would just be that if you went the other way around, you have to use the other area, right, and the other view factor. But it is the same value, same geometric resistance value. Good question. Okay, so let's see. So we have computed our total resistance. We have our emissive power. Now we have this equation that we can solve that actually computes the total heat transfer from I to J, right? So this is sort of the missing piece. And I get it, this is all like a little bit, it lacks an application. I've given you some heat flows, and then we've computed, added an equation here. But just take away from this a general idea that if you're missing equations from your system of equations, you can get them by adding in these sort of energy balances, right? The potential between two nodes as related by a resistance. Any other questions on this before I move on?
Modeling this or something?
Yeah, I think I understand the question. So Blackbody, so the question, if I can kind of repeat it, is we have energy that's coming into and out of our control volume, our thing that we care about, our enclosure. Is that somehow going to affect our Blackbody assumption? And the answer is no. In this case, you have all the surfaces themselves have an emissivity of 1. That means the light that they're emitting is directly related to sigma times t to the 4th. So the fact that heat is coming in or leaving from a given surface across the boundary doesn't change the nature of the Blackbody problem, right? It's still a Blackbody radiation exchange. It's just that when it comes to solving the system of equations, instead of things being equal to 0, they're equal to q dot, right? There's their potential that's related to the heat transfer. So I think with what we'll talk. Good question. Okay. So let's take our radiation surface network. Let me talk about this maybe other case where maybe you have two surfaces in the surroundings. How does that change things? This is sort of a half aside here, but just to quickly go over it. Let's say we have a surface here, we have a surface here, and then we have some surroundings out here. So it's a 3-surface problem, right? But 2 of the surfaces are physical surfaces and 1 is a virtual surface. How does that change things? Well, we can still treat this as like a 3-node problem, where again you have the resistance between each of the nodes like this, and you have emissive power EBI, EBJ. For the surroundings, you can still have an emissive power EBK of that surface, right, that quote surface. It's just that the emissive power is related to the temperature of the surroundings. So it's emitting, the surroundings are emitting to you, but it's something you just sort of deal with this way. So for this type of situation, we would use the enclosure rule. We would treat the surroundings as follows. We would assume that it's a Blackbody. That is, emissivity is equal to 1. We assume the surroundings emit at T surroundings, or we could call it T infinity or T3 or whatever it happens to be, but it's emitting at some temperature. And then in terms of the area is effectively infinite. Right? The surroundings, I guess, by our definition, means that it's just a very large area that's emitting back. So you're receiving radiation, but the view factor from the surroundings to any individual thing is basically 0. Okay, so just to write that out, we would say, like, so F from I to K times AI is equal to F from K to I times AK. So if we solve this for F K to I, that equals FIK, AI over AK. In this case, we're saying AK goes to infinity. So the view factor K to I is basically 0. Right? Just in math, what I just said. All right. All right. So this is a 3-surface problem. What I want to do is, like, it's still maybe a little unclear how you actually take this and implement it in, like, say, an ease program or anything else that you want to solve the problem in.